Hi, everyone. Thank you for being here. We were in the other room until a few seconds ago, so I guess you already did better than us. But we were not late, so we already succeeded our title. So it's my pleasure to be here with Subaru. We will present you some work that has been done in Microsoft on job-level deadline SLOs inside Yarn, so that your jobs are never going to be late again. So a little bit of context. This is a big teamwork. Was Subaru and myself with our manager Shiram from CISL, which is a research group in Microsoft. A few of our friends, Ishai, Nigo, and Jana from the MSR side of Microsoft. And we had a few students helping out during internships as well. So a couple of years back, Subaru and I were on this stage, or one of these stages, presenting Rayon, which is the reservation system that is currently part of Yarn. Nice piece of work, and give you the ability to reserve capacity ahead of time. So you can show up and say, I want 10 containers, I want them for 1 hour, and I want them sometime between now and 9 p.m. Beautiful, give you lots of guarantees. However, had a couple of limitations that when we talk with our friends at other big companies like Yahoo and Twitter or the Hortonworks gang, they were saying, hey, that's awesome, but it's kind of difficult for users to really show up and know exactly what they need to ask for. So how much resources does my job need, and by when do I need to get it done, right? So that was one limitation. And the other one was very simply sort of a social challenge of how do we tell our administrators and our users how to ask for this and how to sort of sell this and kind of switch from this world of queues and priorities to a world in which you can just now say exactly how much resources you want when. So today, we'll present a bunch of new tech that we've been building in the meantime that I would say tackles and I believe solves the first problem. So we will automate the process of figuring out how much resources your job needs, and we'll automate the process of even figuring out when your job needs to complete by. Regarding the social challenges, this is ongoing work inside Microsoft. We're figuring out with our PMs and our partner teams how to deploy this and exactly how to explain our users how to use it. So hopefully in a year or two, we'll be here again telling you how we tackle these other aspects of kind of socializing things. So I will show you lots of doodles that kind of look like this. So I'll introduce it with a little notation. So this is, think about it as the agenda of your cluster, or the plan for what's going to happen in your cluster. X-axis is time. The Y-axis is resources. Of course, we talk of arbitrary yarn containers with complicated resource vectors. My multi-Ds drawing skills are not great, so I'm only going to show one axis. Think about it in terms of memory or number of containers. We're going to talk about a job that have our production job, periodic jobs, and so we're going to have an arrival time. It's marked there with a green A dotted line, and we will have deadlines for these jobs, the red D lines there. We're going to have a certain amount of resources dedicated to these jobs. Those are the yellow box over there. And we're going to have measure actually at runtime what the job actually end up using, right? And this is the squiggly line inside the yellow box. Everything has an I index because those are periodic job. So we're going to have multiple instances of this periodic job. So Ji is going to be the ith execution of the periodic job J. Okay? So with this as our context, what do you think an operator wants, right? So if this is the agenda of my cluster, how would you like the graph to look like if you were a cluster operator? Well, if you're a cluster operator, you care about mostly return of investment, right? Your manager will yell at you if the cluster is not fully utilized. So what we're going to try to look for is something that looks like this, a densely packed schedule. We want this cluster to run hot, right? To be fully busy, fully allocated with all sorts of job running and producing lots of value for the company. And if that's not even enough, right, we have done a lot of work over the years to actually really, really pack this cluster densely. A lot of features that are sort of in the class of work-preserving sharing, right? The notion of queues, the notion of fairness, the notion of opportunistic tokens, right? These are all mechanisms to share the resources even more. So even if I don't have the right to use the resources, I can temporarily borrow them, like our little job is doing down there in the blue spiky part is actually sort of borrowing resources temporarily because no one else is using them in that moment, right? So we have a lot of these kind of mechanics that have been built into our system to really, really squeeze out every single last ounce of capacity from this cluster. And all of this makes operators super duper happy. Now, what do users want? Well, in our experience, we've done a lot of analysis chat with a lot of people, we analyze a lot of the escalation tickets in Microsoft, and what users want is really something very simple. I have a periodic production jobs, I spend a lot of time tuning it and optimizing it, and now I want it to run today like it was running yesterday. I don't want to think about this thing anymore, right? I want it to just keep on doing what it's doing. Please don't bother me, right? So do the user actually end up getting this from our clusters? Unfortunately not. Or fortunately, because then we can solve this problem. So unfortunately, users end up in all sorts of trouble. There's all sorts of unpredictability in our big data clusters. At Microsoft, we see about 25% of our escalations. If you look at them, they're somewhat in the form of, my job was queued today more than yesterday. My job was running slower today than yesterday. Something that more or less echoes complaints regarding predictability of the runs. Sometimes the user is plain wrong about it, but still they complain about unpredictability. And why does this happen? What is the source of unpredictability? There are two big classes, right, that for the purposes of this talk, we're going to group all the sources of unpredictability into two big classes. Things we call sharing-induced unpredictability. These are basically artifacts of how we schedule our clusters, right? So this is because we use opportunistic resources. So sometimes, like on the left side, we're lucky and we get them. And sometimes, like the second execution of the periodic job, well, the cluster was too busy, no free riding for you, right? So you're actually running just on the resource you pay for. And queues as well, right? Sometimes you're lucky and there's no one higher priority than you in the queue in front of you, so you get to run as soon as you submit. Sometimes, well, you know, there was some important guy who was kind of late for some other reasons and your job got pushed out, right? And if that happens enough, you end up having this kind of violation in which your job executes but breaks that dotted red line that we should never pass and misses his deadline. And we'll see that. I'll show you an example of quantifications of exactly how bad it is missing deadlines. And the second class of unpredictability is just a very big melting pot of all the things that are not about scheduling. We call it inherent unpredictability just because that's the rest of the stuff. And these are things like failures, skew, stragglers. We upgraded the hardware. We thought we were going to go faster. It turns out it runs slower for some very particular use of a certain CPU by Spark. We found a slightly faster machine actually runs slower for certain workloads we have. So to quantify this, we ran a TBCH, 10 terabyte scale, 275 node cluster. These are 5 different queries. We ran them in complete isolation. So each one of these run is completely alone on the cluster. There is zero sharing-induced unpredictability. And still, we got a fair bit of unpredictability. Each one of these box and whisker drawing is actually 100 runs of that one job. And you can see that with respect to their average, which is normalized to 1 just for the sake of graphing, we have queries like query Q4 that can be sometimes 30% faster than their average and sometimes over 80% slower than their average. And this is a job that runs the same code on the same data in an empty cluster over and over again. 100 times, so don't tell me about, oh, the first run was cold and the following runs were warm. We exclude the first run, then we run it 100 times on warm data. Still lots of unpredictability, okay? So these seconds, the first source of unpredictability, we're gonna eliminate completely with the work we do today. And inherent unpredictability, we can't eliminate completely, but we can cope with. And we'll show you mechanics. Actually, Subaru will present you mechanics on how we can actually deal with it. So given that this is the world of pain of our users, what do users actually practically do to kind of deal with it? Well, we only give them one tuning knob, right, which is how much capacity they buy. Either is the size of your queue. At Microsoft, we can control the parallelism of individual jobs, so how big are the parallelism dedicated to that individual job. And the user end up doing something like the graph down on the left side, right? So they try to give a very large box for their job, and they try to have a lot of white space around them, right? So trying to basically have no queuing and no other sharing, right? Is that a problem? How big of an effect this is? And this is what we try to quantify with the graph on the right. We took a 50,000 node cluster, 1 month trace. There's about 7 million job instances running. And for each one of them, we're plotting a point in this CDF, which is an empirical CDF, and the point represents the ratio of how much the user provisioned the job for over how much resources were actually used by the job. Ideally, we want to be on that vertical dotted line 1. So 1 for 1, you ask for one, you were planning to run the job with 1 container, and for 1 hour, 1 CPU hour, you get exactly that. In practice, if you see, this curve is very flat, very long. On the bottom left side, there are jobs that are under provision, meaning the user paid, in a sense, for a fraction of the resources they end up using. So it uses a lot of those fair sharing kind of mechanics. And on the right side of the ideal line, there are all the jobs that were sort of requesting lots of resources because I want to make sure my job runs. In practice, my job uses only a small fraction of them, right? And you can see sometimes by a very, very large margin, like 10 times, right? Part of this is the peak over average ratios of the actual job execution, and Subra will comment on that. So this seems a pretty bad place, right? So the problem is, with the existing system, it looks like we almost need to trade off utilization for predictability. We're in this kind of ugly spot in which it looks like a zero-sum game, right? The more we make the cluster highly utilized, the more we introduce sharing, induce unpredictability, the more the users are desperate and they try to over-provision their job, they lower our utilization, we fight back with some new trick. That's a pretty ugly spot to be. So what's the opportunity that we have? How can we solve this problem? Well, the key idea here is we're going to leverage the repeating history of our cluster. We're going to have lots of these jobs are periodic production jobs, so very highly predictable. They do kind of the same thing every day or every hour. And we're going to try to use this to drive a smarter way of doing scheduling. Now, are we always going to be right? Well, of course not, right? So we have also to be able to dynamically course correct. So we will have done a lot of predictions and planning, and then we will dynamically fix up the few runaway jobs that were actually behaving differently than we thought. So with this, let me introduce a big overview of the approach. The internal nickname of this is Morpheus. We have an OSDI paper on this if you're interested in a bunch more details than we can present today. What we do, we start from the raw logs, right? So things about yarn logs, HDFS logs, application level logs. And from these, we extract 2 core pieces of information. One is a provenance graph. So this is a graph that represents all of the data dependencies between all of the jobs that we run in our cluster, including ingress and egress operations. And the other one is telemetry history information, right? So think about the skyline of resources that a job consumed, or at what time the job was started, at what time it was writing to a certain output file, right? So this piece of information, in a sense, captures very precisely the history of what happened in our cluster in terms of data dependencies as well as resource consumptions. And we crunch those through a bunch of techniques that we're going to present throughout the talk. And we extract basically a representation of what the user wants and how much resources does it need for that, right? So we will automatically derive what is the arrival time and deadline for a job. And we will automatically derive what is the skyline of resources that this job needs, okay? Once we do this, now we need to take a lot of objects that look like this, a lot of periodic reservations, and try to place them in the agenda of our cluster, right? So we need to do this well because otherwise we're going to get bad utilization, right? So we're going to try to squeeze them in like a Tetris kind of game and try to put as many jobs as we can in a small amount of space. And if the world was a perfect place, we would be done, but in practice it isn't. So sometimes our predictions were wrong, or something went, the job changed, the user submitted, updated their software, and now things run a little faster, a little slower than before. So we dynamically reprovision the amount of resources that are given to the job. So we stare at the job while it runs, and we compare what the job is requesting to do right now versus what we were planning to give to the job. And we figure out dynamically, hey, shall I give you a bit more parallelism now, or shall I give you a little more time to finish the stage of execution we're in, or are we good and what we planned was fine, right? And by doing this, we actually can repair and get really good SLO attainment, really good success in meeting the deadlines. So with this kind of big overview, let me start tackling one of the first hard problems, which is how we derive deadlines automatically. Right? And Subaru then is going to tackle the other sort of difficult core challenges and present a few experiments that kind of demonstrate all the effectiveness and draw some conclusions. So, okay. So to extract a deadline, we stare really hard at our provenance graph, right? And in particular, we look at a job A. This is a periodic job, runs, for example, every day. And the consumers of the output of job A. In this case, B and Z. And we particularly care about B because this is the guy that typically runs first after A, right? And so what we do, we're going to plot, I'm going to plot in this time of the day plot an histogram that shows all of the completion times for A in blue and all of the start times of B in green, right? So if you see, A starts at some point earlier and typically finishes between 5 and 7 a.m. Then nothing really interesting happened until 2 p.m., where job B typically is scheduled and starts. Some of the run of B are going to be delayed a little bit because of queuing, so they're not going to start in the 2:30 bucket of this drawing. So we're going to model all of these as random variables. We're going to look at the different percentiles, and we can derive from this something that says, well, it looks like 2 p.m. or 14 in this graph is actually really representative of when the output of A is typically consumed. I'm going to call this the deadline for job A. Because if you think about it, it doesn't matter when job A finishes if no one is looking at your output. So until job B touches the outputs and reads it for the first time, it doesn't really matter if I ran job A or not, right? So the predictability the user cares about is really finishing by whenever time someone else is going to read my output. Anything in between, it's hidden, it's invisible to the user, it doesn't really matter. So I'm going to call this a deadline, right? And I'm trying to sell it to you as like, oh, this is the real deadline for the job. But I need to do a bit of a better job, right? I need to prove you that this is actually a deadline, right? So what is a deadline? A deadline is a point in time that separates a really good, happy behavior, I finished by my deadline, I feel good, to a really bad behavior. Oh my God, I missed my deadline, the world is going to melt, right? How we measure this we use the same trace that I was describing before, many millions of jobs of 50,000 machines, and we measure empirically the conditional probability of job B to fail, given whether A succeed and completes by the deadline, succeed but miss the deadline, or fail completely. And drum roll, good news. If A missed the deadline, this is just as bad as if A completely failed and didn't produce his output. So the amount of failures that we observe in B is just as high if A misses what we call a deadline or completely doesn't run at all, right? And this is about 4 times worse of the number of failure in B if A completes by what we call a deadline. So this is telling us that this random point in time we're calling the deadline for A is actually really demarcating 2 important different behaviors. A happy A completing, B running happily and successfully, or A kind of running long and finishes after the deadline, B failing, right? The second thing that is important is not just that these are real deadlines, but that we can do something intelligent with them, right? If we were just deadlines, but we couldn't really make them actionable, sure, you just measure a bunch of things in your data sets and you cannot really do anything useful. So when is a deadline useful? A deadline is useful when there's a lot of slack, right? When the job runs, like the example we did before, the job runs and finishes in the morning, and then I have a lot of time before anyone consumes the output. And why is it useful? Because it means I can actually move the job in different moments in time, right? And it will really not matter to the user because I'm finishing by what the deadline is, right? So if I have this, it means that in my Tetris game, I have a lot of flexibility. I can move jobs around and really find really beautiful ways in which they stack together really, really tightly, and we get better utilization. So again, same big, large workload that we described before. We show here a CDF of the amount of slack that we have, so completion time to the deadline, divided by the duration of the job, right? This is just to put things in perspective because we have some really very long job and very short jobs. So a value of 1, it really indicates a job that is taking just as much slack afterwards as it takes to run. So we can run it one more time, right? And so you can see that 70% of jobs have at least a value of 1, sometimes a value of 10, sometimes a value of 100 or even more, right? So this means we have a lot of slack in this workload that we can play with to really dense things pack densely our allocations. With this, I conclude. I let Subaru take over and present the rest of the hard problems we tackle and some interesting experiments.
Sorry, the mic just, yeah, so I'll just hold it. Thanks, Carlo. So Carlo talked about how we derive the deadline. So once you have the deadline, what is the next challenge we have? That is to make sure that the job, thank you. There you go. Yeah, thank you. So once we have the deadline for the job, we want to make sure that the job gets the resources it needs to meet the deadline. That's the next challenge for us. And how do we go about doing that? So knowing what resources a job needs is a very hard problem. So how we determine that is we use the past resource usage of the job, the history, because our job is periodic. It has run many times in the cluster. And like Carlo mentioned, we have the telemetry. So it's like, think of it like the timeline service data. So using that, we try to find a skyline of resources which kind of envelop what resources a job needs. And I'll just call out a few things. Why do we use the term skyline? Any job, a non-trivial job, has multiple stages, and different stages need different resources. Let's take the simplest job which runs in our cluster. It's a MapReduce. And you have a map stage and a reduce stage. And as all of us know, we need a lot different resources for mappers versus reducers, right? So, and to illustrate this, we have on the graph, we have 4 runs of a job, so which are the light gray lines, which are R1, R2, R3, R4. And we have kind of shifted the time, aligned them to 0 to see the different runs are using slightly different resources, and we can kind of stack them to see it. And as you can see, 3 of the runs, which are the normal runs, they use very similar resources, the ones on the lower, R1, R2, R3. And you have R4, which is like a straggling, it's like a runaway instance, which happens, we know that once in our job, most of the time runs fine, but once in a while, you might have some unpredictable, you might have some hardware failure, some straggler, so that job, as you can see, takes a lot more resources. And what we try to do is use the history and come up with this dark black line, which is our skyline, which is kind of what is the optimal resources which a job needs to make sure that it meets its deadline, right? So how do we do that? We actually do a very simple intuition. We have a linear program which does it. So we have 2 things which can go wrong, right, in any job. It's the intuition, again, very simple. You can either under-allocate, that means give the job less resources than it needs, which is here, where on the lower side, where you have less resources than the job needs, or you can, on the lower side, you have over-allocation because the jobs R1, R2, R3 run, and you have, in our black line, we have actually given a little bit of buffer, slightly more buffer resources than it needs. And on the for R4, which is our runaway job, we have actually done under-allocation. That means we have allocated less resources than the job needs, right? So these are the 2 things which can go wrong. So what we do in the linear programming model is very simple. We want to minimize under and over allocation, right? So how we do that is we have an alpha parameter to tune it. So I'll just talk about that. So what is this alpha parameter? So this alpha parameter tells us, right, what is the tolerance we have for the beating the SLO versus utilization, right? So for example, certain jobs are very high priority. So we will have very low alpha so that we make sure that we have buffer to meet those. So that means the utilization, because that means we're over allocating, so utilization is slightly down. And in other conditions, we can have the other way. These jobs are good, so we'll give a very tight skyline for those resources. So there's a chance that you can have SLO violation, but your utilization is much higher because we're densely packing those jobs, right? To give an example, this is a small alpha. That means in this case, we just take R4, right? Very close to R4. That means all the 4 runs, we have enough resources to make sure all the 4 runs meet the deadline. But that means for R1 and R2, R3, we are giving a lot more resources than those runs need. So we are doing an over allocation. And on the other hand, you could have higher alpha, in which case you actually track closer to R1, R2, R3, and then the runaway instance may not have the resources it needs to complete. So, but we do have a solution for that, which I'll just be talking about it. Before I get into that, so now we talked about how we derive the skyline, right? So how well does it work? So this is a graph which demonstrates how well we work. And this is the same data set which Carlo mentioned. It is from our production cluster, 1 month of a production cluster. So it's a 50,000 node cluster, which is one of the large production clusters. So we have about 100,000 periodic jobs and about 7 million instances of those runs of the jobs. Here, what we are plotting is the resources with the job needs. So the red dotted line is the ideal one. So that means you're giving the job the exact number of resources which it needs to complete. What we have plotted is how much resources the user has provisioned for the job versus what the system has come up, automatically derived skyline, right? So let me first start with the user. So anything to the left of the red dotted line, that means we have underallocated. And anything to the right, we have overallocated. So the blue dotted line is the user. As you can see in the bottom, there's a little bit of underallocation, but there's a lot of overallocation. So if we take the 80 percentile job, we are overallocating about 20 times. So think about it. This is actual production traces from our cluster. We are overallocating 20 times what the job needs, okay? But I don't want to just throw shade at the user, right? We are the users, including all of us, right? So why is this happening? This is again just reiterating what Carlos said, right? First, it's a very, very hard problem to know how many resources your job needs. We all run jobs. There is an optimization going on under the hood and all of that. Hive changes daily. There is joins, so you never know what the join is going to explode data. You have filters, you have where clauses filters, you don't know how well they work. So it's very difficult to determine, it's a very difficult problem to know what resources you need. And there's another problem, like this is coming to the skyline. Jobs have multiple stages. A query has a lot of MapReduce. Oozie workflow has a lot of jobs. So this problem of knowing the resources just gets exponentially harder because you have so many stages, and subsequent stages depend on what happens in the previous stages, right? So what generally we have noticed what user tends to do is they just fix one number for the whole job and just put the rectangle. So that causes a lot of inefficiencies. So that's why if you see the lines for Morpheus, which is a red and dotted green lines, we do much better because we actually derive a skyline for the jobs. So let's start with the alpha, like we mentioned, let's start with, first let's start with the 80 percentile, right? So if you see, we are doing about 1.5 times, we are over provisioning a little in this area. We are about 1.5 times what the job needs. So from 20, we have much better. So if you take the alpha, let's take the conservative alpha. That means we are very conservative so that you meet your SLO. There we are about 1.5 times. So, and if you take the green, we are a little better. We are about 1.3, 1.2 times. So coming from 20x, we are a lot better. But if you look at the green, so going down to the left, we do a little bit of, compared to the blue, with the conservative alpha, we do even less under provisioning than the user. But with the more aggressive green alpha, which is better because we do a lot less over provisioning, but we do end up doing a little more under provisioning than the user. That means there's a chance the job may not get all the resources it needs, so there is an SLO violation chance, right? But it's not all bad. So we have a mechanism to correct for that. So let me talk about that. So this is called dynamic reprovisioning. So the idea is, again, very straightforward, easy to understand. What we do is we get the predicted skyline from our LP model, and then we actually watch the trace of the job, run actual execution of the jobs very closely. So in our example, if you think about 2 slides back, for R1, R2, R3, we are very good because they are the normal runs and our skyline gives enough resources for them. And when we have a run, which is a runaway run like R4, what we do is we actually adjust the resources for the job when it's executing. So this is more like increasing the parallelism or giving it more resource, like more extending the time duration for which it needs resources, etc. So this is a dynamic reprovisioning. And I'll illustrate this by giving a specific example. So in this graph, we have like 100 runs of TPCH query 1, okay? The query 1 is pretty simple. It has 2 map phases followed by the two reduce phases. And what we observe is the second phase of the map once in a while tends to have stragglers. So all of us have run MapReduce, and we know that once in a while you have some few stragglers which prevents the reducers from starting, right? So these stragglers from really going on. So the reducers themselves, they're pretty consistent. So what we do in this case is we just extend the map. So we just extend the map stage resources, kind of just give it more time when we see it straggling. So we know the progress of the map which is reporting. So we just extend, okay, it should be now 100%. but it's not, it's only 60%, so we just extend that stage and allow it to meet. And that's what we call as dynamic reprovisioning, and is illustrated by this black box. So this is a very simple, as you can see, it's a very simple model we use, but we see it's very quite effective. There are a lot more complicated work, which is a very hot research space. So there's a lot more work being done there, which can be plugged in very easily. So now we have the resources which the job needs, and we also have this dynamic reprovisioning. So what we need to now do next is reserve those resources. So we have this YARN reservation system. That was YARN 1051. So we could just go and reserve those resources, right, using the reservation system, because that's what it does. There's one point here, which is our jobs are periodic jobs. So just taking the example, we had like 100,000 periodic jobs, but we had 7 million instances. So that means we have to store 7 million instances of resources reserved for the jobs, which is not very efficient, right? So storing millions of instances. So what we do is, let's look at this example. So we have job 1, which runs every other hour at the odd hours. So it runs at 1 p.m., 2 p.m., and 3 p.m. And we have job 2, which runs the other alternate hours, 2, 4, 6. And we have job 3, which runs every hour, 1, 2, 3, 4, right? So now what we do is, we just find out the LCM, the least common multiple of these jobs, which is 2 hours. That means for job 1, we store its odd 1 o'clock, and job 2, we store its even. And for job 3, since it runs every hour, we need to store 2 instances. But this is the same pattern which will repeat, because if you look at it. So all we need to do is just store the LCM and say this keeps repeating. Okay? So that's all we store. So it becomes a very concise representation. And we have an added advantage here, like what Carlo mentioned, right? What the users want is very simple. Let my job just run as it always runs, right? So here what happens with this model is, we always reserve the resources for the job at the same time. So this job will always repeat at the same time, so you have predictability. So it will always run at the same time, right? So this is our added. And this is again going back to our production traces to just demonstrate that this falls nicely within this model. So we have a lot of jobs which are like in the minutes, and then we have the largest jobs which are at 1 day. So if you have a LCM of 1 day, you just store that data and you can repeat it unto infinity, and all you need to store is 1 day's data, right? So now we'll put together all of this, right? And just to say, this is like a simulated run because we have millions of instances, and it's a trace from a very large cluster. So this yellow arc is what we can control. This is a knob we have, right? The alpha knob. So as you can see, on the x-axis of the cluster is the cluster footprint. So how much size cluster do you need? So if you have better packing, you can reduce the clusters, right, to run the same jobs. And then on the y-axis is our SLO attainment. So how much SLO do we violate, right? And this red dot is our baseline, and the baseline is 1, which is our actual production run, right? So as you can see, we have a wide range of knobs which is possible. So we start with, like let's say we are very aggressive. That means you start with alpha, which is high, very high, 5%, and with static, no dynamic reprovisioning, essentially. What we can do is we can reduce the cluster size by 65%. But the chances you have about 40-odd% extra, more SLO violations. But we can get better. So what we want to do ideally is stay to the left and below the deadline, right? So that means you are below means you are doing more SLO, better SLO guarantees than what is the baseline. And to the left means you are having better cluster utilization. So that is possible with other values. And if you look at like one of the sweet spots, which is having alpha 1% in dynamic. So here we have better cluster utilization, 15% better cluster utilization with about 13x reduction in the deadline misses, right? So it is up to the operator now to tune the cluster. So we allow the operator to tune the cluster to whatever he wants, and we can allow this, right? Do this. So this is how we make sure that we have resolved the tension between the utilization and the SLO getting predictability for the user, right? So till now we talked about traces and doing simulations. We didn't stop there, so we actually have polished and hardened the code. So this is like some of the highlights of the work we did. So for basic thing, we need high availability, so we integrated this with the RM high availability. And then we did some performance work. So actually, we use some run length encoded data structures so that the data structure is better. And we have read-write locks because very few writes are only when the user asks for the reservation. And then we do a lot of reads. And then all of the data structures, the agents who do the placing and all of them use the run length encoded data structures. You have a cost-based placement guy who's the Tetris game, right? How do you place the blocks? The blocks are different weird shapes because each user has different skylines. So we use a cost base. So think of it like the Uber search pricing, but just the opposite. Search pricing is bad because as the demand goes up, you pay more. So we want to avoid that clash of the demand, so we kind of spread out. So that's the cost-based placement we do. So we added like a lot of documentation because it's a non-trivial so that users can easily bootstrap. So in Microsoft, we have a lot of non-Java clients, so we added REST stuff. And we talked about the simulations. So this is extension to SLS. SLS is a scheduler load simulator. So it simulates, it runs an entire RM in memory, and you can simulate load on the scheduler. We integrated the reservation system into that, and the periodic reservations. And then one of the cool small things we did is add invariance checker. What is the invariance checker? It actually checks for the correctness. So because we know we are running things and job completes, does it mean it's correct? This guy actually checks for certain invariants to make sure it's correct. So these are the work which are done. So, but we have a lot more work to do. So if you guys feel enthused about it, please join. And this just a calling out a few. So one of the things is priority. So currently we just do a first come first serve basis, but we know that not all jobs are equal. So we want some of them. So we are adding priority, and we are adding a lot more metrics to see what is happening under the hood. How is the cluster behaving? And then we are also working on visualization for this, right? So once we had all of this, we wanted to actually do some scale testing. So we took a sample of our cluster trace and add a souped up version of GridMix which can do reservations and ran it on a small cluster, which is 2,700 nodes. And to get it running with all of this, we had to do some locking fixes on the scheduler. And on the right is the graph. So what we are actually plotting is the cluster utilization versus how much the blue lines talks about the utilization. And just to keep it simple, we use the memory to act as a proxy of the cluster utilization. So we had about 80 terabytes of memory for the cluster. And the preemption is just we measure as a proxy for how wrong we went, right? If we made a wrong decision, like if we didn't allocate the resources correctly, more preemption would be happening. That's the red line, right? So as you can see, we are keeping the cluster pretty much pegged, and we have very little preemption. So it's working out pretty well. To summarize, what we presented is 3 key ideas, which is like automatically derive SLO based on historical runs. Then rely on recurring reservations to make sure that you get your SLO, meet your SLO, and then dynamically reprovision to handle inherent unpredictability. So this essentially we demonstrated that we can resolve the tension between predictability and utilization. So with this, we conclude our talk and open up for questions.
Might have time for one question.
Maybe two.
Thank you. So you mentioned that this is for a regular scheduled jobs. So have you done experiments on a cluster which has, of course, a lot of clusters have regular scheduled jobs, but they also take a lot of ad hoc loads.
Sure.
How does it interplay with existing ad hoc loads? And one other question, just as a two-part. In the previous graph, just the previous slide, the graph you showed, the performance seems to kind of, the preemption seems to increase around the last few hours. Does it degrade over time, or is it just an anomaly?
So let me answer this first. This is just a random, whatever the randomization of where stuff arrives. And some of the jobs are very large, so can kick in a larger amount of problems in a small window. Answering the first question, all we do can handle always both reservation, periodic job with reservation, non-periodic job with reservation, as well as ad hoc jobs. So this plays very nicely with the capacity and fair scheduler. So you can take all of your queue structure and say, this one queue, I want it to be reservable, and I want to do all this game that we described for that one portion of your capacity, while another queue or the rest of your queues can run arbitrary ad hoc jobs. So what we guarantee actually is And there's the standard sort of overcapacity fair sharing. So if we book some resources for these and we don't use them, all your doc jobs can use them. But when we're getting close to the deadline and we need these resources, preemption kicks in and will like knock you out and make sure that this guy completes. So it's been designed exactly to handle both, actually.
Anyone else?
Hi, so the question is about the dynamic reschedule part. Like when the job runs actually slower than what you expect, then you need to occupy space afterwards, right?
Yeah.
What if it's already been packed like tightly? Do you have to redo the bin packing like for everything afterwards?
Sure.
So right now, we are talking about unpredictability. It's a very good question. So we have not talked about compaction. So what we just do is, once the job is completed, we just completely finish the reservation. But we could do it at stage level, right? So we could think about if this stage completes before, can we early do the next stage? We haven't done that, but it's possible.
But furthermore, right, so the idea is a small amount of general global buffer can be multiplex across multiple jobs that run fast or slow. Because typically you don't have all of your jobs spiking all over the same time, right? It might happen, but it is not incredibly common. Second is the fact that we have in the cluster also a lot of ad hoc jobs. The idea is if a big reservation production important job needs extra capacity, it's okay for him to grab more resources and we will sort of delay or not run some other jobs. And third is the priority work we're describing, it's also designed for the same reason. So potentially what we're going to do is to say, this is the most important job in the universe, right? In the case of Twitter is tweet serving, right? If tweet serving was run as a service on top of this, it will say, oh, that guy needs to spy. I don't care what everything else is planned to happen. This guy will need to spy. So we will be able to possibly leverage this slack that we have in the deadline to move some jobs around. But if that's not possible, too bad. We will kill some of the lower priority guys. The big advantage is that instead of having everyone starving a little and everyone missing their deadline by a little, we can very explicitly say, we will kill one guy and everyone else complete by their deadline, right? So these are all policy decisions, right? You can either have everyone suffering a little, it's an option that we have, or you can simply say, no, I promise SLOs, I'd rather have one guy be murdered and everyone else running on time, right? That's kind of the trade-offs you have.
Thank you again, gentlemen.
Thank you.
Thank you, guys.